Hello and welcome to Standalone at Scale, ironic take on high-performance computing with Timothy Randles, Jacob Anders, and myself, Julia Krieger. So one question one might ask is, why ironic? And ultimately it's because physical hardware in data centers are never going to go away. You're always going to have the physical hardware in the racks inside data centers. And really, it's not because you can make data centers look really cool. But in order to build anything, you need a foundation, you need infrastructure to build upon, you need a substrate. And in computing technology, the hardware is always going to be the foundation that you're going to build upon. So there's also some really solid reasons for having your own bare metal hardware. First one's latency. And if you look at how long it takes for data to travel in 1 millisecond, it's about 124 miles, or 200 kilometers. That's inside a piece of fiber or a piece of copper. And that excludes intermediate hardware like retransmitters and switches and routers. So if you were exchanging 1 kilobyte of data every millisecond for 100 seconds, you'd have 100 megabytes of data transferred. Whereas if you're doing the same with 30 milliseconds of latency, you'd only have 3.3 megabytes. And then also, when we talk about having your own data centers, usually there's really solid reasons why for a business or organization. One is data sovereignty, which is becoming a major topic due to newer regulations, required security measures, and these measures can come from anywhere. Contracts, legal, local or regional laws, even court orders, and often these are driven by industry or government security needs in order to keep data safe and ultimately move whatever forward. But when you start looking at also bandwidth of interconnects, while we've seen a massive explosion from the first local area network technology in the 1980s, we can see that local Ethernet has always been faster than wide area networking. And it's always kind of chasing, but these are also exponential growth graphs. And largely because the telecom industry takes upon leverages those same technologies for interconnects. So we end up eventually getting that same level of connectivity. But when you have it locally and you have the same piece of hardware, you obviously have a huge advantage. But again, when you're building these data centers, there's some infrastructure that's required. Lots of construction, lots of work goes into building these facilities for very good reasons. So when we talk about why ironic, it provides a RESTful API interface. It encodes common practices in managing physical hardware fleets. There's integration with OpenStack and other tools like Ansible and Terraform. And it's scalable and production proven. Ultimately, we turn weeks into minutes and hours. So now with why ironic for HPC, I'll hand it over to Jacob.
Thank you, Julia. A typical high-performance computing system is large. It consists of hundreds to thousands of nodes, sometimes tens of thousands. And it is also highly optimized so that classic HPC workloads, by saying design batch queue jobs, run very well. The price to pay for this degree of optimization is limited flexibility. It might be hard to run non-standard workloads on an HPC system. For example, let's look at cybersecurity research or research involving sensitive clinical data. It would be rather difficult to carve out a set of nodes, put them in an isolated network, and do some independent work on that. Due to this, I see great degree of potential for improvement in terms of flexibility of high-performance computing. Just as a comparison, let's have a look at enterprise computing, which has changed very significantly over the last years with adoption of cloud and DevOps. HPC had evolution in this period, but definitely not a revolution. Looking further into adoption of cloud and high-performance computing, we see there has been some of it, but not as much as some have anticipated. Cloud is used for cloud bursting to increase scale beyond what's available on-site, it's also been used as supplementary capability to support those non-standard workloads I referenced earlier. However, many clouds are still running on virtualized platforms, and that introduces performance overheads, which are something undesirable in HPC. It also adds some complexities around fast access to storage, which Julia has mentioned. Lastly, cloud computing systems are complex, and so is OpenStack. And when we add bare metal components and software-defined networking for bare metal, the complexity grows even more, making it not trivial to build and maintain such system. Let's look further into some of the difficulties that HPC centers encounter while trying to adopt cloud computing approach to HPC. First of all, as I mentioned earlier, HPC systems tend to be very large. Importantly, they also tend to run at very high loads. All of this together means that problems are more likely to happen, and when they happen, they're more complex to solve. This in turn means that an HPC facility would need a sizable and very skilled team to troubleshoot those issues. Now, while having such capability in terms of expertise is something natural for cloud hosting companies because running clouds, for example, OpenStack clouds is their core business, that doesn't necessarily apply to HPC facilities because their core business is something different. It's procuring, building, and optimizing very large batch queue systems. And they can't necessarily afford diverting a high number of their staff to cloud computing work. But the good news is there is a potential solution to this. We believe that Ironic Standalone can help solve those problems and provide a resilient platform to build upon, allowing HPC facilities to implement infrastructure as code on bare metal without introducing great degree of complexity. Because of taking the standalone approach, we might occasionally encounter challenges along the lines of features that aren't fully present or implemented. However, the good news is that those features can essentially just move higher up the stack and be implemented using configuration management tools that's leveraging the bare metal cloud built with Ironic Standalone. All in all, this means that the entry-level requirement in terms of complexity is significantly reduced, and HPC centers now have a tool that's much more likely to succeed in the circumstances they operate in. Lastly, I would like to highlight key features of Ironic Standalone that make it particularly suitable for HPC workloads. First of all, obviously performance. Because of its nature, running on bare metal, Ironic workloads will run as well as they run on classic batch queue systems, and same optimization methodologies can apply. However, performance is also something we can look at in terms of provisioning speeds, and this is where Ironic excels as well. We can use diskless provisioning, which is quite common in high-performance computing, but we can also use highly optimized disk-full provisioning using features such as fast track, which means that we've got nodes on standby already booted into the provisioning run disk waiting for provisioning requests to come through. Second very important feature of Ironic, scalability. Ironic uses a concept of conductor groups, so essentially as the environment grows, we can add instances of conductor, and each of them can manage a subset of nodes, letting the environment grow horizontally, potentially to a very large scale. And with this, I would like to hand over to Tim, who will give us user's perspective on what Ironic Standalone can do at the National Laboratory.
Thank you, Jacob. I'm Tim Reynolds from Los Alamos National Laboratory. I work in the HPC design group. So how are we thinking about using Ironic at Los Alamos? Firstly, the lab's been around for a long time. It started as Project Y in 1943 as part of the Manhattan Project. But today it's an all-encompassing science and engineering laboratory supporting our main mission, which is stockpile stewardship. We also do a number of other scientific realms, such as physics, biology, material science, energy and health. And high-performance computing is integral to LANL's mission today. Our simulation-based stockpile stewardship is how things evolved starting in the early 90s when we stopped actually testing our nuclear weapons in the United States. But we also do a lot of climate modeling, vaccine discovery, material science, and other things that are require the capabilities of high-performance computing. And we have a long history of computing at LANL. Initially, during the Manhattan Project, our computers were actually people. We went through the vacuum tube and switchboard programming eras, the control data machines of the late 60s and early 70s. We had the first Cray supercomputer, the Cray 1 serial number 1. We entered the massively parallel era at the lab. And this is when things really started to change for us because the scale of our operations completely blew up. We weren't just running a few small machines. We were running an integrated whole of thousands of nodes. And today we're in the hybrid era, as encompassed by Roadrunner and Trinity. Here we have a picture of Trinity and Roadrunner. Each one of those machines is quite large. LANL has a number of HPC clusters, more than 10, ranging in size from 32 nodes to more than 20,000 nodes in the case of Trinity. And the bottom picture there is Roadrunner. To give you a sense of scale, the footprint of Roadrunner is about 1/3 of an acre. We also have to run a lot of other services to support these systems. So we have tens of petabytes of file systems and a whole plethora of other support services that we need. So in my own words, LANL's HPC mission are to provide the services and compute cycles that our users need and ensure that those services are maximally available. If the users aren't able to run on our systems, what good are our systems? But the complexity of our environment and the desire to maximize uptime means that we have very conservative system management processes and practices. My manager at the lab is fond of quipping that the way we run our machines was 5 years ahead of its time 15 years ago. And we're still using software such as CF Engine and Perseus for configuration management and provisioning. If you go look these things up, CF Engine is still alive, Perseus is long dead. In fact, go look at the original Perseus website to find out just how dead. And over time, these practices, while they're robust, have become inefficient. It takes us a lot of time to do some fairly simple things. So right now we have a project underway to modernize our operations. It's our next generation systems management project, creatively named. We're using Ansible to replace CF Engine for our configuration management. Ansible is well understood. It's grown up in the DevOps era. There's quite a lot of mindshare out there. It's a Red Hat product now. And we don't quite yet know what we're going to do to replace our Perseus provisioning system, but we do have a set of requirements, such things as it be API driven, it be highly scalable, it have a modular architecture, it be able to provision a wide range of systems from diskful systems to diskless systems. Like I said, we're using Ansible, so it'd be nice if it integrated well with Ansible. It needs to support a large range of hardware, not only in scale and capabilities, but also in age. So interfaces for system management such as IPMI are still available, but new things like Redfish are coming along. And it needs to be built with the modern world in mind and actively supported. And I think that Ironic fits the bill for all of our requirements. So what are some of the benefits of Ironic for us? One, it should be one service to rule them all. Today, since we have a lot of different systems with different characteristics, we have just as many different ways of provisioning and managing those systems. And because of that, we'd like to get one tool that can handle everything that we've got. And I think Jacob did a good job of showing that, we can do diskful and diskless, we can deploy to a RAM disk, and it can scale out. We need a modern approach to image management deployment. Ironic provides this. It can deploy over a simple HTTP interface, and it's easy just to keep dropping new files into an HTTP server and then being able to deploy those to our systems. It has a very active and supportive development community, and many different ways to interact with that community. I'm fond of talking with Julia and Jacob all the time on the IRC channel they use. Standalone services, the fact that Ironic can be used standalone and it doesn't require OpenStack is really attractive to us because, as Jacob said earlier, we're not really in a position to take on managing all of the cloud stuff that may go along with something like Ironic. But the good thing is Ironic is well integrated with OpenStack. So if we go down the road of adopting more cloud technology inside of our data centers, Ironic's already there, ready to provision that cloud system as well as it is our HPC system. So I really think that Ironic is going to enable LANL HPC to be responsive and innovative with our system management, providing our users with world-class computing in support of their world-class science achievements. Thank you.